Hey there, welcome to Sparx Science for Sleep. Take a deep breath and settle into your cozy blanket, letting worries slip away like stars at dawn. I'm thrilled you're here for a gentle journey through the cosmos, where science turns into a soft bedtime story. This video will help you drift off to sleep, but if you're still awake, you'll learn something cool about the universe. Tonight, we're exploring what it might mean to hear from an alien intelligence out there in the starry unknown. Science is like a glowing lantern, lighting up the universe's secrets. Picture yourself floating in a safe, warm space, stars twinkling above. Close your eyes if you'd like, or let your gaze soften in the dim light. Where are you listening from? Drop a comment with your location and the time. Now, let your mind drift like a cloud, ready to glide into a tale of cosmic whispers, starting with a signal that once sparked wonder in the night. Take a slow, deep breath and let your body soften into the quiet of this moment. As we drift from that starry hill where the universe whispered its secrets, let's glide into a story that began on a warm summer night in 1977, when a signal reached out from the darkness, like a single note in a cosmic lullaby. It was called the WOW signal, a fleeting murmur from the stars, caught by a massive radio telescope known as the Big Ear at Ohio State University. Picture a giant dish, turned upward like a curious ear, listening to the vast night sky. That night, the telescope picked up something extraordinary, a signal 30 times stronger than the usual hum of the cosmos, lasting just 72 seconds. It came from the constellation Sagittarius, a cluster of stars that sparkles like a distant lantern in the heavens. The astronomer Jerry Eman, poring over the data, saw the signal's strength printed as a string of letters and numbers, 6EQUJ5, so striking he circled it in red ink and wrote "Wow" beside it. This wasn't just static or noise, it was sharp, focused, like a deliberate tap on the shoulder from somewhere far away. Scientists scrambled to rule out earthly sources, radio stations, satellites, even passing planes, but none fit. The signal stood alone, a mystery that felt like the universe had just winked at us. Now, let's linger on that moment as the quiet of the night wraps around you. The Big Ear was part of a grand quest to listen for signs of intelligent life beyond Earth, a project rooted in the hope that we're not alone. Radio telescopes like this one work by catching radio waves, invisible ripples that travel across space, carrying information from distant stars. Unlike light, which can be drowned out by the glow of cities or clouds, radio waves cut through, clear and steady, like a whisper that travels for light years. The WOW signal was unique because it matched what scientists expected from an alien transmission: narrow, strong pulse, not the broad static of natural cosmic sources like pulsars or galaxies. It was as if someone, somewhere, had tuned a cosmic radio to just the right frequency, broadcasting for a brief moment before fading back into silence. Jerry Eman and his team spent weeks trying to find it again, pointing the telescope back at Sagittarius, but the signal never returned. It was a one-time visitor, leaving behind a question that still hums in the minds of astronomers today. As you settle deeper into this calm, let's think about what that signal meant. The Big Ear wasn't just a machine, it was a symbol of human curiosity, a giant ear tilted toward the stars, hoping to catch a conversation. In 1977, the technology was simple compared to today, but it was enough to spark wonder. The telescope scanned the sky in a slow, patient sweep, collecting data on paper printouts, not fancy screens. Each night, it listened to a different patch of the cosmos, sifting through the static for something that stood out. The WOW signal did just that. It was like finding a single clear note in a storm of noise. Scientists checked for comets, planets, or even secret military tests, but nothing explained it. The signal's frequency, centered around 1,420 megahertz, was special to it, known as the hydrogen line, a natural frequency where hydrogen atoms emit radio waves. Any civilization advanced enough to send a signal might choose this frequency, like picking a universal language that any starfaring species could understand. It's as if the signal was a postcard, written in a cosmic alphabet, mailed from a place we can only imagine. Let's pause here, in the stillness of this story. The WOW signal wasn't just a blip on a screen, It was a moment that made people look up and wonder. Could it have been a beacon, sent by a civilization light years away, or perhaps a natural phenomenon we don't yet understand, like a cosmic firework that flared and vanished? The astronomers who studied it didn't jump to conclusions. They checked their data, tested their equipment, and searched again, but the signal remained elusive. This careful approach is what makes science so beautiful. It's a slow dance with the unknown, each step deliberate, each question a spark of light. The WOW signal's home in Sagittarius adds to its allure. That constellation, shaped like an archer, is near the heart of our Milky Way, a dense region teeming with stars. If life exists out there, it's a place where it might thrive, surrounded by countless suns and planets. The signal's brief appearance, just 72 seconds, feels like a whisper that stopped just as we leaned in to listen. Now, as you rest in this quiet moment, consider the scale of that night in 1977. The Big Ear was one of many telescopes in a growing effort to search for extraterrestrial intelligence, a movement that started decades earlier. Scientists like Frank Drake and Carl Sagan believed that if life exists elsewhere, it might use radio waves to communicate, just as we do with our radios and TVs. The WOW signal was a glimpse of what that search could find, a moment that felt like the universe was reaching out. Its intensity, 30 times stronger than the background noise, was like a shout in a silent room. Yet, because it never repeated, it remains a puzzle. Some say it could have been a comet's radio emission, discovered years later, but others hold on to the possibility that it was something more, a message from a mind we can't yet fathom. The truth is, we don't know, and that's okay. Science thrives in the unknown, like a seed waiting to bloom in the dark. Let's drift a little further into this tale. The WOW signal wasn't just a scientific event. It was a spark that lit up imaginations. Newspapers ran headlines, people talked about aliens over coffee, and astronomers doubled down on their search. The signal's code, 6EQUJ5, became a kind of cosmic graffiti, a mark left by something we couldn't see. Each letter and number in that sequence showed the signal's strength, peaking at U before fading away, like a wave rolling back from the shore. The Big Ear couldn't pinpoint the exact source, only a general direction, because it was fixed, scanning the sky as Earth turned. But that limitation only adds to the mystery, like hearing a voice in the dark but not knowing where it's coming from. Scientists have looked at that patch of sky countless times since, with better telescopes, but the signal remains a singular event, a moment frozen in time. As the night wraps around you, think about the people behind that discovery. Jerry Eman wasn't a famous name before that night, just a scientist volunteering his time, sifting through data under the quiet hum of fluorescent lights. His wow wasn't just excitement, it was a human reaction to something vast and unknowable. The team at Ohio State worked in a world before computers filled every desk, relying on paper and patience to decode the universe's whispers. Their work was part of a broader dream, one that started in the 1960s with the first searches for extraterrestrial signals. The WOW signal gave that dream a jolt, a reminder that the universe might be more alive than we think. It's humbling to realize how small we are, yet how bold building machines to listen to the stars, hoping for a conversation that might span light years. Let's ease into the science of how that signal was caught. Radio telescopes like the Big Ear are marvels of engineering, designed to pick up the faintest ripples in the cosmic sea. They don't look like optical telescopes with their shiny lenses. Instead, they're giant dishes, sometimes miles wide, that collect radio waves and focus them into a receiver. The Big Ear was 2 football fields long, its flat and tilted reflectors working together to scan the sky. When a signal hits the dish, it's amplified and turned into data, like translating starlight into numbers. The WOW signal stood out because it was narrowband, meaning it stayed on one specific frequency, unlike the broad noise of natural sources. Think of tuning a radio in your car. You slide through static until a clear station comes through. That's what the WOW signal was, a clear station broadcasting for a moment before slipping back into the static. Now, let's linger on the mystery of its origin. Sagittarius, where the signal came from, is a bustling part of the Milky Way, home to billions of stars and possibly just as many planets. If an intelligent civilization sent that signal, they'd need technology far beyond ours, a transmitter powerful enough to beam a message across light years. The hydrogen line frequency, 1420 MHz, is a clever choice for such a message. Hydrogen is the most common element in the universe, and its radio emissions are a universal constant, like a note every scientist in the galaxy would recognize. If aliens were sending a signal, they might pick this frequency to say, "Hey, we know the rules of the cosmos too." But the signal's silence since 1977 keeps it enigmatic. Was it a one-off transmission, like a ship passing in the night, or something natural we've yet to understand, like a cosmic hiccup? As you sink deeper into this story, let's explore why the WOW signal matters. It wasn't the first signal astronomers noticed, nor the last, but it's the most famous because it checked so many boxes for what an alien signal might look like. It was strong, narrow, and came from space, not Earth. Yet, its fleeting nature 72 seconds and gone makes it a tease, a hint of something grander. Scientists have proposed all sorts of explanations, from natural phenomena like comets to more speculative ideas like a distant civilization testing their radio. In 2017, some suggested a comet passing through the telescope's view could have caused it, but the debate continues, as comets don't typically produce such sharp signals. The WOW signal's power, 30 times the background noise, suggests something deliberate, but without a repeat. It's like a single word in a conversation we never heard again. Let's soften into the context of that time. In 1977, the search for extraterrestrial intelligence, or SETI, was still young. NASA had funded early efforts, but the field was seen as a long shot, almost a dream. The Big Ear was one of the few tools dedicated to this quest, built in the 1960s to map the sky's radio emissions. Its discovery of the WOW signal was a fluke, a moment when the right telescope was pointed at the right spot at the right time. The signal's duration matched the telescope's scan time, as it moved with Earth's rotation, catching the signal as it peaked and faded. This alignment was perfect, almost too perfect, like a cosmic coincidence designed to make us pause. The astronomers didn't celebrate right away. They checked their data, looked for errors, and tried to replicate the signal, but it was gone, leaving only questions. Now, as you rest in this gentle narrative, think about the signal's journey to reach us. If it came from a civilization, it could have traveled for hundreds, maybe thousands of years. Light travels fast, 186,000 miles per second, but space is vast. A signal from Sagittarius, even just a few hundred light years away, would have left its source long before humans invented radio. Imagine a civilization sending a message, not knowing if anyone would hear it, like a bottle tossed into the cosmic ocean. The WOW signal's strength suggests a powerful source, perhaps a beacon meant to be noticed, or maybe an accidental burst, like a radio tower left on by mistake. Its mystery lies in its silent Cincino encore, no follow-up, just a single, unforgettable note. Let's ease into the technology that made this moment possible. The Big Ear was a marvel for its time, a giant structure of metal and wire, built to catch the universe's faintest whispers. Radio astronomy was still growing in the 1970s, a field that let us see the cosmos in ways our eyes never could. Radio waves don't need clear skies or dark nights. They pierce through dust and gas, carrying stories from the farthest reaches of space. The WOW signal's frequency, the hydrogen line, is a quiet spot in the radio spectrum, free from much cosmic noise, making it a perfect channel for a message. Scientists chose to listen there because it's a frequency any advanced species might use, like a cosmic meeting place. The signal's clarity, rising and falling in a bell-shaped curve, matched the telescope's movement, as if it was waiting to be heard. As the quiet of the night surrounds you, consider the human side of this discovery. Jerry Eman wasn't looking for fame. He was a volunteer, spending late nights analyzing data, driven by curiosity. His wow was a moment of pure wonder, a scientist's heart skipping a beat. The team at Ohio State worked in a small, cluttered room, surrounded by stacks of paper and the hum of old computers. They weren't chasing headlines, they were chasing truth. The WOW signal gave them a glimpse of something bigger, a hint that the universe might hold more than stars and gas. It's a reminder that science isn't just machines and number sets, people, dreaming, questioning, and reaching out. The signal's mystery has inspired generations, from astronomers to storytellers, all wondering what it meant and what might come next. Let's drift a bit more into the signal's place in history. The WOW signal came at a time when humanity was just starting to explore space in earnest. The Voyager probes had launched that same year, carrying golden records with messages for any intelligent life that might find them. The idea of contacting aliens wasn't just science fiction, it was becoming science fact. The WOW signal felt like a reply, a nudge from the cosmos saying, maybe you're on the right track. Its impact went beyond the lab, sparking debates about whether we should keep listening or start sending our own signals. Some worried about revealing our presence, while others saw it as a chance to join a galactic conversation. The signal's brevity, 72 seconds, makes it all the more tantalizing, like a half-heard whisper in a crowded room. Now, let's soften into the science of listening for such signals. Radio telescopes don't just hear, they translate the universe's energy into data we can understand. The Big Ear used 2 reflector-sewn flat, 1 curved toe bounce radio waves into a receiver, like catching rain in a bucket. The WOW signal's strength was measured in signal-to-noise ratio, a way to compare it to the background hum of the cosmos. Its peak, marked by the U in 6EQJ5, was like a flare in the dark, unmistakable and fleeting. Scientists have since used more advanced telescopes, like the Allen Telescope Array, to search for similar signals, but none have matched the WOW signal's clarity. Its frequency, tied to hydrogen, is a universal marker, a place where minds across the galaxy might meet. The signal's origin, whether natural or artificial, remains a question that keeps us looking up. As you rest in this calm, let's think about the signal's legacy. It's not just a data point, it's a symbol of our desire to connect. The WOW signal has inspired books, movies, and countless late-night conversations. It's a reminder that the universe is vast but not empty, and that our search is just beginning. Scientists haven't given up. They've looked at Sagittarius with every new telescope, hoping for another clue. The signal's mystery is its power. It doesn't give answers, but it asks questions. Was it a deliberate message, a fleeting broadcast, or something else entirely? The lack of a repeat doesn't dim its importance. It fuels our curiosity, like a single star guiding a ship through the night. Let's glide toward the end of this story, as the night holds you gently. The WOW signal is a piece of a larger puzzle, one we're still piecing together. It's a moment when the universe seemed to speak, even if we didn't understand the words. Its discovery showed us what's possible when we listen, when we build tools to hear the cosmos and hearts to dream of what's out there. As you lie there, cozy and calm, let the signal's mystery linger, a soft echo in your mind. It's a reminder that science is a journey, not a destination, and each step brings us closer to understanding our place among the stars. Now, let's drift to another corner of this cosmic tale, where the search for life continues, with telescopes scanning the heavens for the next whisper from the dark. Let's take a slow, deep breath, and let the quiet of the night wrap around you like a soft blanket. As we drift from the mystery of that fleeting WOW signal, a single whisper from the stars, we glide into a broader tale of humanity's endless quest to listen for voices in the cosmos. This is the story of SETI, the search for extraterrestrial intelligence, a mission that began decades ago and continues to hum with hope, like a lighthouse sweeping its beam across a vast, dark sea. Picture a field in Northern California, where the Allen Telescope Array stands, its cluster of dish antennas gleaming under the moonlight, each one turned upward like a cupped hand waiting for a message. These telescopes are our ears to the universe, listening for signals that might hint at life beyond Earth. SETI started in the 1960s, sparked by scientists who believed that if intelligent life exists out there, it might use radio waves to communicate, just as we do with our radios and walkie-talkies. The idea is simple but profound. In a galaxy with billions of stars, surely some harbor civilizations advanced enough to send a hello across the void. The search is like looking for a single pearl in an ocean of sand, patient and persistent, driven by the dream of connection. SETI's work began with pioneers like Frank Drake, who in 1960 used a radio telescope in West Virginia to listen to 2 nearby stars, Tau Ceti and Epsilon Eridani. It was called Project Ozma, a nod to a fictional princess from a far-off land, and it set the stage for decades of listening. The telescopes used in SETI are marvels, designed to catch faint radio waves that have traveled light years to reach us. Unlike optical telescopes that capture light, these dishes collect invisible ripples, translating them into data that scientists can study. The Allen Telescope Array, built with help from philanthropist Paul Allen, is a modern marvel, with 42 antennas working together like a choir, each tuned to a different part of the radio spectrum. They scan the sky day and night, sifting through the cosmic static for a signal that stands out, sharp and clear, like a note held steady in a storm of noise. The goal is to find something deliberate, not the random hum of stars or pulsars, but a message crafted by a mind we can't yet imagine. The science of SETI is both patient and precise. Radio waves are perfect for cosmic communication because they travel at the speed of light and can pass through dust clouds that block visible light. The frequency SETI often listens to, around 1,420 MHz, is the hydrogen line, a natural hum of the universe where hydrogen atoms emit a faint signal. It's a quiet spot in the radio spectrum, like a clear channel where an alien civilization might choose to broadcast, knowing any advanced species would notice it. Imagine tuning an old radio, sliding through static, until a voice comes through. SETI does that, but for the entire galaxy. The telescopes sweep across thousands of stars, collecting data that computers analyze for patterns. A natural signal, like one from a quasar, spreads across many frequencies, but an intelligent signal is narrow, focused, like a laser beam cutting through fog. The WOW signal was one such candidate, but SETI's mission is to find more, to catch a signal that repeats and confirms we're not alone. Now, let's linger on how SETI works in practice. The Allen Telescope Array is designed to scan millions of stars, far more than the Big Ear could manage in 1977. Each antenna is a 6-meter dish, small but powerful, working together to cover a wide swath of the sky. They're controlled by computers that sift through billions of radio channels, looking for anything unusual. This isn't a quick process, it's like reading every page of a library to find a single misspelled word. The data comes in as numbers, not sounds, and scientists use algorithms to spot patterns that don't match the natural hum of the cosmos. If a signal is found, it's checked against known source satellites, airplanes, even microwave events to rule out earthly interference. The dream is to find a signal that persists, one we can track back to a specific star, maybe even a planet. The Allen Array, with plans to grow to 350 antennas, is a step toward that dream, a network of listeners waiting for the universe to speak. The story of SETI is also a story of people, not just machines. In the 1980s, NASA funded a SETI program called the High Resolution Microwave Survey, but in 1993, a senator cut the funding, calling it a waste of money. Undeterred, scientists formed the SETI Institute, a non-profit that keeps the search alive through private donations. People like Jill Tarter, a leading SETI astronomer, have spent decades listening, driven by the belief that the universe is too vast to be silent. The work is slow, often thankless, but it's fueled by curiosity, like a child staying up late to watch the stars. SETI isn't just about finding aliens, it's about understanding our place in the cosmos. Every signal analyzed, every star scanned, is a step toward answering the question, are we the only ones asking these questions? The telescopes, with their quiet hum, are a testament to human hope, reaching out across light years for a connection. Let's ease into another layer of this tale. SETI doesn't just listen, it invites everyone to join the search. In 1999, the SETI at Home project began, letting people around the world help analyze data using their home computers. Imagine millions of screensavers crunching numbers from the Arecibo telescope in Puerto Rico, each one a tiny piece of the cosmic puzzle. Over 5 million people have joined, from students to retirees, all part of a global effort to find a signal. It's like a worldwide treasure hunt, where the prize is a message from the stars. The Arecibo telescope, a giant dish nestled in a Puerto Rican valley, was a key player until it collapsed in 2020. Its data, still being studied, holds years of cosmic whispers waiting to be decoded. SETI at Home showed that the search isn't just for scientist sites, for anyone who looks up and wonders what's out there. The technology behind SETI has grown leaps and bounds since the days of the big ear. Modern telescopes can scan thousands of frequencies at once, covering more of the sky than ever before. The Allen Array, for example, can listen to multiple stars simultaneously, like eavesdropping on a dozen conversations at once. It's designed to be flexible, adapting to new discoveries about where life might exist. Scientists now know that certain types of stars, like those similar to our Sun, are prime targets because they're stable enough to support planets with life. The search focuses on these stars, but it's not limited to them. SETI scans everything from red dwarfs to giant stars, just in case. The data is so vast that artificial intelligence is now used to sift through it, spotting patterns humans might miss. It's a blend of old-school astronomy and cutting-edge tech, all aimed at catching the next wow signal. As we linger in this quiet moment, let's think about why SETI matters. The universe's vast Milky Way alone has about 100 billion stars, and there are billions of galaxies beyond it. If even a tiny fraction of those stars have planets with life, the numbers are staggering. SETI's job is to narrow that down, to find the one signal that says, "We're here." It's not just about finding aliens, it's about proving that intelligence can thrive in the cosmos, that we're part of something bigger. The search has its skeptics. Some say it's like looking for a needle in a haystack the size of a planet. But every star scanned, every signal checked, is a step toward understanding. The Allen Telescope Array, with its dishes spread across the California landscape, is a symbol of that persistence, a quiet promise to keep listening, no matter how long it takes. Let's soften into the details of how SETI chooses its targets. Not every star is a good candidate for life. Stars like our Sun, called G-type stars, are ideal because they burn steadily for billions of years, giving planets time to develop life. Red dwarfs, smaller and cooler, are also promising. They're the most common stars in the galaxy and can host planets in their habitable zones where liquid water might exist. SETI focuses on these zones, sometimes called the Goldilocks zone, where conditions are just right for life as we know it. The telescopes scan thousands of these stars, looking for signals that repeat or show patterns, like a cosmic Morse code. The process is slow, methodical, like panning for gold in an endless river. But each scan adds to our knowledge, mapping the radio sky in ways that help future searches. The history of SETI is filled with moments of hope and frustration. After Project Ozma, scientists tried bigger experiments, like the Soviet Union's searches in the 1960s and NASA's efforts in the 1980s. Each failure to find a signal taught us something: how to filter out noise, how to focus on the right frequencies, how to dream bigger. The wow signal was a high point, a reminder that something might be out there, but it also showed how hard the search would be. A signal that doesn't repeat is like a ghost, intriguing but hard to prove. SETI's strength is its refusal to give up, even after decades of silence. The Allen Telescope Array, with its sleek, modern design, is built to listen longer and deeper, covering more stars than ever before. It's a quiet rebellion against the idea that we're alone, a belief that the universe has stories yet to tell. Let's drift into the challenges SETI faces. The universe is noisy. Stars, pulsars, and black holes all emit radio waves, creating a background hum that can drown out a signal. Scientists use clever tricks to filter this noise, like looking for signals that stay on one frequency or show a Doppler shift, a change in frequency that suggests a source orbiting a star. The Allen Array is designed to do this automatically, scanning millions of channels in seconds. But even with this technology, the odds are daunting. A civilization would need to be transmitting at the exact moment we're listening, and their signal would need to reach us across vast distances. It's like trying to hear a whisper from the other side of a mountain. Yet, SETI persists, driven by the idea that even one confirmed signal would change everything. The people behind SETI are as fascinating as the science. Jill Tarter, inspired by the novel Contact, dedicated her life to the search, becoming a voice for persistence and wonder. She and others at the SETI Institute work with limited budgets, relying on donations and passion to keep the telescopes running. Their work is a blend of patience and optimism, like planting a seed you may never see grow. They're not just looking for aliens, they're exploring what it means to be human, to reach out and ask if anyone else is doing the same. The Allen Telescope Array, with its dishes spread across a quiet valley, is a monument to that dream, each antenna a silent question sent into the night. The search has grown since the 1960s, from one telescope to a global effort, with observatories in Australia, China, and beyond joining the quest. Let's ease into another aspect of SETI's work. Beyond listening, some scientists advocate for active SETI sending our own signals into space, hoping for a reply. In 1974, the Arecibo telescope sent a message toward the star cluster M13, a binary code describing human life, our DNA, and our solar system. It was a bold move, like shouting into the void, knowing the message won't reach its target for 25,000 years. Active SETI is controversial, like Stephen Hawking, worried it could attract unwanted attention, like leaving your front door open at night. But others believe it's worth the risk, a way to join the cosmic conversation. SETI's primary focus remains listening, but the idea of sending messages adds another layer to the search, a reminder that we're not just passive observers, but active participants in the universe's story. As we linger in this gentle narrative, consider the scale of SETI's ambition. The Milky Way has about 100 billion stars, and recent discoveries suggest most have planets. If even a tiny fraction of those planets host life, the possibilities are endless. SETI doesn't expect to find a signal tomorrow. It's a long game, played across decades. The Allen Telescope Array is built for that marathon, with plans to expand and listen to 1 million stars in the coming years. Each star is a chance, a tiny spark in the dark that might hold a civilization. The search is methodical but hopeful, like a poet writing lines for an audience they may never meet. The data collected fills hard drives, waiting for the day when a signal stands out, clear and unmistakable, like a melody rising from the silence. Let's soften into the legacy of SETI. The WOW signal was a spark, but SETI is the fire, burning steadily through the years. It's inspired generations of scientists, writers and dreamers, all wondering what a signal might mean. Would it be a simple hello, or a library of knowledge from a civilization thousands of years old? The search has changed how we see ourselves, reminding us that Earth is just one small world in a galaxy teeming with possibilities. The Allen Telescope Array, with its quiet hum in the California night, is a bridge to that future, a tool that might one day catch the signal we've been waiting for. Until then, it listens patient and tireless, a symbol of our hope to find others out there sharing the same starry sky. Now, as the night holds you gently, let's glide to another chapter of this cosmic tale. The search for signals is just the beginning. What about the worlds those signals might come from? Let's drift toward the story of planets like our own, scattered across the galaxy, each one a potential home for life, waiting to be discovered in the quiet of the cosmos. Take a slow, deep breath, and let the stillness of the night cradle you gently. As we drift from the quiet hum of SETI's telescopes, their dishes turned toward the stars like eager listeners, we now glide into a new chapter of this cosmic story, one that takes us to the worlds that might hold life. Imagine a vast ocean of stars, each one a sun with its own family of planets, some perhaps glowing with the soft green of life, like distant islands in a boundless sea. This is the tale of the Kepler mission, a space telescope launched by NASA in 2009 to hunt for planets beyond our solar system, places where life might thrive. Picture Kepler as a silent sentinel, orbiting the sun, its gaze fixed on a patch of sky in the constellations Cygnus and Lyra, watching for the faint flicker of planets passing in front of their stars. The mission revealed thousands of worlds, many resembling Earth, each one a potential stage for stories of life we can only dream of. These discoveries have changed how we see the universe, showing us that planets are as common as grains of sand on a beach, scattered across the galaxy, waiting to be explored. The Kepler mission was a game changer, a telescope designed not to look at stars, but to find the shadows of planets. It used a technique called the transit method, watching for tiny dips in a star's light when a planet crosses its face, like a moth passing before a lantern. These dips are small sometimes, just a fraction of a percent, but Kepler's sensitive instruments could detect them, revealing planets thousands of light years away. By staring at over 150,000 stars for years, Kepler found more than 2,600 confirmed exoplanets, with thousands more candidates waiting to be studied. Many of these worlds sit in the habitable zone, a region around a star where temperatures allow liquid water to exist, a key ingredient for life as we know it. These zones are like cosmic sweet spots, neither too hot nor too cold, where oceans might ripple under alien skies. The discovery of so many Earth-like planets suggests that our galaxy, the Milky Way, could hold billions of worlds where life might take root, each one a quiet possibility in the vastness of space. Let's linger on how Kepler worked its magic. Launched on the 6th of March, 2009, from Cape Canaveral, the telescope was a marvel of precision, equipped with a photometer that measured starlight with incredible accuracy. It focused on a single patch of sky, about the size of your hand held at arm's length, containing millions of stars. By monitoring these stars continuously, Kepler caught the subtle changes in brightness that signaled a planet's transit. Each dip in light told a story the size of the planet, its distance from the star, even the length of its year. Some planets were gas giants, like Jupiter, but others were rocky, Earth-sized worlds, orbiting stars at just the right distance for life. The data poured in, filling computers with numbers that astronomers turned into maps of distant systems. Kepler's findings showed that planets are everywhere. Most stars have at least one, and many have several, orbiting in delicate dances around their suns. The habitable zone, often called the Goldilocks zone, is where Kepler's discoveries shine brightest. This region varies depending on the star. Hotter stars have habitable zones farther out, while cooler stars, like red dwarfs, have them closer in. Red dwarfs are the most common stars in the galaxy, making up about 3/4 of the Milky Way's stellar population. They're small, dim, and long-lived, burning for tens of billions of years, giving any planets in their orbit plenty of time for life to evolve. Kepler found that many of these stars host rocky planets in their habitable zones, some even smaller than Earth. One standout was Kepler 452 billion Reals, announced in 2015, a planet about 60% larger than Earth, orbiting a Sunday-like star 1,400 light-years away. Its orbit, 385 days long, places it in a zone where liquid water could pool, perhaps forming oceans under a sky we can only imagine. Such worlds are like lighthouses, guiding our search for life. Kepler's discoveries didn't just count planets, they reshaped our understanding of the cosmos. Before the mission, we knew of only a handful of exoplanets, found through ground-based telescopes using different methods, like watching stars wobble from a planet's gravitational tug. Kepler's transit method was more efficient, revealing planets by the thousands. Its data suggested that about 1 in 5 Sunday-like stars has an Earth-sized planet in its habitable zone, a number that translates to tens of billions of potential Earths in our galaxy alone. This abundance is staggering. Imagine a Milky Way where every 5th star has a world that might hold forests, rivers, or even cities. The mission showed that our galaxy is a crowded place, not just with stars but with planets, each one a quiet stage where life might play out its own story, perhaps sending signals like the ones SETI hopes to catch. Let's soften into the details of Kepler's work. The telescope didn't just find planets, it categorized them, giving us a census of the galaxy. Some planets were super-Earths, rocky worlds larger than ours but smaller than Neptune, a type we don't have in our solar system. Others were hot Jupiters, gas giants, orbiting so close to their stars that their surfaces glow with heat. Kepler also found systems with multiple planets, like Kepler 11 Reals, a star with 6 planets packed tightly together, their orbits closer than Mercury's to our Sunday. These discoveries showed that planetary systems are diverse, not cookie-cutter copies of our own. Some stars have planets in orbits so tight they whip around in days, while others have worlds that take years to complete a single loop. This variety suggests that life, if it exists, could take forms we can't yet predict, thriving in conditions we might find strange. The mission wasn't without challenges. Kepler's telescope had to be incredibly stable, holding its gaze on the same stars for years. It used reaction wheels like tiny gyroscopes to keep its aim steady, but by 2013, 2 of these wheels failed, threatening to end the mission. Scientists got creative, using the pressure of sunlight to stabilize the telescope, launching a new phase called K2. This allowed Kepler to survey different parts of the sky, finding hundreds more planets. The mission ran until 2018, when its fuel ran out, but its data is still being studied, revealing new planets years later. The effort involved thousands of scientists, from engineers who built the telescope to astronomers who pored over its data, all working together to map the galaxy's hidden worlds. Their work is a testament to human ingenuity, turning a small spacecraft into a window on the cosmos. Let's drift into what Kepler's findings mean for the search for life. The discovery of so many Earth-like planets makes the idea of alien intelligence more plausible. If billions of planets have the right conditions, liquid water, stable climates, the right chemistry, life could be common. Scientists estimate that the Milky Way might have millions of habitable planets, each a potential home for microbes, plants, or even advanced civilizations. Kepler didn't just find planets, it gave SETI a roadmap, pointing telescopes towards stars with promising worlds. For example, the star TRAPPIST-1, found later by other telescopes but inspired by Kepler's work, has 7 rocky planets, 3 in the habitable zone. Such systems are prime targets for future searches, places where a signal might one day be heard, echoing across the light years. The science of finding exoplanets is a delicate art. The transit method relies on luck. A planet must cross its star from our point of view, and not all do. Kepler's patch of sky was carefully chosen, rich with stars but not too crowded, so each could be studied clearly. The telescope's photometer measured light with such precision that it could detect a change smaller than a light bulb dimming in a city. Each transit had to be confirmed multiple times, as false signals like star spots or binary stars could mimic a planet's shadow. Astronomers used follow-up observations with ground-based telescopes to verify Kepler's finds, ensuring the data was solid. This careful process turned raw numbers into a catalogue of worlds, each with its own story, a planet baked by its star, another cloaked in clouds, perhaps one with oceans glinting under alien sunlight. Kepler's legacy goes beyond numbers. It showed us that our galaxy is a place of possibility, where Earth-like worlds are not rare, but plentiful. This shifts the odds for SETI's search. If there are billions of potential homes for life, the chances of finding a signal grow. Scientists now focus on stars with Earth-like planets, especially those close enough for us to study in detail. The Kepler data also helps refine the Drake equation, a formula we'll explore later, which estimates how many communicative civilizations might exist. By giving us a better count of habitable planets, Kepler makes that equation less of a guess, grounding our dreams in data. The mission's discoveries have inspired new telescopes, like TESS, the Transiting Exoplanet Survey satellite, which continues the hunt, looking at brighter, closer stars. Let's linger on a few of Kepler's standout discoveries. Kepler 186f, found in 2014, was the first Earth-sized planet in a habitable zone around a red dwarf 500 light-years away. Its star is cooler than our Sun, so its habitable zone is closer, but the planet might have a climate suitable for life. Another gem, Kepler 22 billion reals, is a super-Earth orbiting a Sunday-like star with a year lasting 290 days. Its size suggests it could be a water world, covered in oceans deeper than Earth's bracketing. These planets, and thousands like them, are more than data points, they're invitations to wonder. Could they have skies filled with strange colors, creatures swimming in alien seas, or even cities lit by unfamiliar stars? Kepler doesn't answer these questions, but it opens the door, showing us that the galaxy is rich with places where such stories might unfold. The mission also taught us about the diversity of stars. Red dwarfs, the most common, are now prime targets because they're so numerous and long-lived. A planet around a red dwarf might be tidally locked, with one side always facing its star, creating a twilight zone where life could thrive. Kepler found many such planets, some so close to their stars they orbit in days, others farther out, where time moves more slowly. This variety challenges our assumptions about where life can exist. On Earth, life clings to extreme places, volcanic vents, frozen tundra, so why not on a planet with a permanent sunset? Kepler's data suggests that life could adapt to countless environments, each world a unique experiment in the chemistry of existence. As we ease into this story, consider the human effort behind Kepler. Thousands of scientists, from those who designed the telescope to those who analyzed its data, worked together across years. Volunteers, through projects like Planet Hunters, helped spot planets in Kepler's data, proving that this quest belongs to everyone. The mission faced setbacks, equipment failures, budget cuts, but persisted, like a ship sailing through a storm. Its success came from precision and patience, qualities that define science at its best. The data Kepler collected is a treasure trove, still yielding new planets as computers grow faster and algorithms sharper. It's a reminder that discovery is a slow dance, each step revealing a bit more of the universe's vast choreography. Let's soften into the broader impact of Kepler's work. Before the mission, we could only guess how common planets were. Now we know there are everywhere more planets than stars in the Milky Way. This abundance changes the search for life, making it less a shot in the dark and more a focused hunt. SETI now points its telescopes at stars with known planets, especially those in habitable zones. The data also informs astrobiology, the study of life's potential in the cosmos. Scientists look for biosignatures, gases like oxygen or methane, that might hint at life on these worlds. Future telescopes, like the James Webb Space Telescope, can analyze the atmospheres of exoplanets, searching for these signs. Kepler's legacy is a map of possibilities, guiding us toward worlds that might one day answer our signals. The story of Kepler is also one of scale. The Milky Way is 100,000 light-years across, with 100 billion stars, each a potential sun for its own system. Kepler's patch of sky was just a tiny sliver, yet it found thousands of planets. Extrapolate that across the galaxy, and the numbers are mind-boggling: billions of worlds, millions inhabitable zones. This vastness makes the silence of the cosmos, the lack of confirmed signals, all the more intriguing. If planets are so common, why haven't we heard from anyone? This question, known as the Fermi paradox, we'll explore later, but for now, let's bask in the wonder of Kepler's discoveries. Each planet a quiet hope, a world where life might whisper back. As the night holds you gently, let's think about what these planets mean for us. They're not just dots of light or numbers in a database, they're places, real and tangible, orbiting stars we can see in the night sky. Some, like those around TRAPPIST-1, are close enough 40 light-years away that we might one day study them up close. Others, thousands of light-years distant, are beyond our reach but not our imagination. Kepler showed us that the galaxy is a garden of worlds, each with its own story. Could one of them hold a civilization, looking back at us, wondering if they're alone? The mission's data is a gift, a catalogue of places where the next wow signal might originate, waiting for us to listen. Now, let's glide to another chapter of this cosmic tale. We've explored the worlds that might hold life. Now let's consider the messages we've sent to them, our own whispers into the dark, hoping to start a conversation across the stars. Take a slow, deep breath, and let the quiet of the night settle around you like a soft veil. As we drift from the distant worlds revealed by Kepler, those shimmering islands in the cosmic sea, we now turn to a different kind of outreach: humanity's attempt to speak to the stars. This is the story of the messages we've sent into the vastness, like letters cast into a boundless ocean, hoping someone somewhere might read them. Imagine a golden record, glinting in the dark of space, carrying the sounds and sights of Earth, a snapshot of who we are, etched in metal and launched aboard the Voyager spacecraft in 1977. These messages, crafted with care, are our way of saying hello to the universe, a gesture of hope that some distant mind might one day hear our voice. From simple radio signals to intricate recordings, humanity has been whispering to the cosmos for decades, each message a blend of science, art, and dreams, sent to bridge the gap between our small world and the infinite unknown. The Voyager Golden Records are perhaps the most famous of these cosmic letters. Launched on Voyager 1 and 2 from Cape Canaveral, these records were designed to last 1 billion years, a time capsule for any civilization that might find them. Picture a 12-inch disc, plated in gold, tucked inside a protective aluminum cover, engraved with instructions for playback. The records hold 115 images, encoded as analog signals, showing Earth's landscapes, animals, and people scenes of mountains, oceans, and a child's smile. They also carry sounds, a 12-minute montage of Earth's noises, from crashing waves to a baby's cry, and greetings in 55 languages, each a soft hello from humanity. Music, too, fills the disc's Sparx Brandenburg Concerto, a Navajo chant, a Peruvian panpipe melody, and Chuck Berry's Johnny B. Good, a vibrant mix of our cultural heartbeat. Astronomer Carl Sagan, who led the project, chose these elements to paint a picture of Earth's diversity, a message of peace sent to the stars. The idea behind the golden records was simple yet profound. If intelligent life exists, it might stumble across these spacecraft, drifting far beyond our solar system. The records were a collaboration between NASA and a team of scientists, artists, and musicians, each piece carefully chosen to represent humanity. The images include diagrams of our DNA, a map of our solar system, and even a sketch of how humans reproduce, all encoded in a way that an advanced civilization might decode. The sounds capture Earth's essence: wind, rustling through trees, the rumble of thunder, the laughter of children. The greetings, spoken in languages from Amharic to Wu, offer a chorus of welcome, with phrases like "peace to all" and "we wish you well." The music spans cultures and eras, from Beethoven's Fifth Symphony to a Japanese shakuhachi flute, a tapestry of human creativity meant to resonate across light years. Let's linger on the science of these messages. The golden records were built to endure the harshness of space, where radiation and micrometeorites could erode most materials. Gold was chosen for its durability, and the records were encased in aluminum jackets with a cartridge and needle for playback. Instructions on the cover, etched in simple symbols, show how to play the record and decode the images, using the hydrogen atom's transition time as a universal clock. The records also include a map, using pulsars rapidly spinning neutron stars as cosmic landmarks. Pulsars emit regular pulses of radio waves, like lighthouses in space, and their positions are so precise that an alien civilization could use them to pinpoint Earth's location in the Milky Way. This map, a clever blend of astronomy and navigation, ensures our message has an address, even if it takes 1,000,000 years to be delivered. The Voyager messages weren't the first we sent. In 1972 and 1973, NASA launched Pioneer 10 and 11, each carrying a small gold anodized aluminum plaque. These plaques, designed by Carl Sagan and Frank Drake, were simpler, but just as meaningful. They feature drawings of a man and woman standing in front of the spacecraft for scale, their hands raised in a gesture of peace. The plaques also show a diagram of our solar system, with the sun's position relative to 14 pulsars, and a line tracing the spacecraft's path from Earth. The idea was to give any finders a sense of who we are and where we come from, like a note tucked into a bottle before it's tossed into the sea. The Pioneer plaques were a bold first step, a way to say, we're here, to a universe that might be listening. Another milestone came in 1974 with the Arecibo message, sent from the Arecibo radio telescope in Puerto Rico. Unlike the physical plaques and records, this was a radio signal, beamed toward the star cluster M13, 25,000 light-years away. The message, crafted by Frank Drake, was a binary code, a series of ones and zeros that could be decoded into a grid of 1,679 bits. When arranged, the grid forms a picture, like a pixelated sketch, showing numbers 1 to 10, the atomic numbers of life's key elements: hydrogen, carbon, nitrogen, oxygen, phosphorus, and a diagram of DNA's double helix. It also includes a simple drawing of a human, the population of Earth, and a sketch of the Arecibo telescope itself. Sent at a frequency of 2,380 megahertz, the message took 3 minutes to transmit, a brief burst of data aimed at a distant cluster of 300,000 stars. It was a symbolic act, more a proof of concept than a practical message, but it showed we could speak to the stars. The Arecibo message was a leap in active SETI, the practice of sending signals rather than just listening. Unlike passive SETI, which waits for a cosmic whisper like the wow signal, active SETI is proactive, broadcasting our presence to potential listeners. The message was sent using Arecibo's powerful 1 megawatt transmitter, strong enough to be detected across vast distances, though it won't reach M13 for 25,000 years, and any reply would take just as long to return. The binary code was chosen because it's a universal language any civilization advanced enough to receive it would understand binary, the foundation of digital communication. The message's content was kept simple, focusing on math and science, like a cosmic handshake that says, "We understand the universe." 2. It's a reminder that communication across species requires a shared foundation, something as basic as counting or the structure of atoms. Let's soften into the challenges of crafting these messages. Communicating with an alien civilization isn't like sending an email, it's a puzzle wrapped in a mystery. We don't know what kind of beings might receive our signals, what senses they have, or how they think. Would they see images the way we do? Would they hear music, or would it sound like noise? The Voyager team chose sounds and images that reflect human experience, but an alien mind might interpret them differently. The golden records include a tutorial with diagrams showing how to play the disc at 16 2/3 revolutions per minute, a speed chosen to fit all the data. The pulsar map uses the spin periods of 14 pulsars, measured to 9 decimal places, to locate Earth within a few light years. This precision ensures that even millions of years from now, the map will still point to our Sunday, a beacon for anyone who finds it. The choice of content for these messages was a delicate balance. For Voyager, Carl Sagan's team spent months debating what to include. They wanted to show humanity's best creativity, our diversity, our curiosity, without overwhelming or confusing a potential recipient. The music ranges from classical to folk, chosen for its emotional depth rather than popularity. The greetings, recorded by people from around the world, reflect Earth's linguistic mosaic, from ancient Akkadian to modern Mandarin. The images show everything from a supermarket to a dolphin, a mix of the mundane and the profound. The team avoided political or religious symbols, focusing on universal themes like life and learning. The Arecibo message, by contrast, was purely scientific, using math and chemistry to describe us, a choice that assumes aliens value the same principles we do. It's a gamble, but one rooted in the belief that science is a common language across the cosmos. The effort to send these messages wasn't just technical, it was deeply human. The Voyager records were a labor of love, with contributions from musicians, linguists, and everyday people. Anne Druyan, a key member of the team, recorded her brainwaves and heartbeat, hoping to share the rhythm of a human mind. The Pioneer plaques were simpler, but their creation involved artists and astronomers working together to distill humanity into a single image. The Arecibo message was a celebration of the telescope's power, sent during a ceremony to mark its upgrade in 1974. These projects show how science and art intertwine, creating messages that are as much about us as they are for others. They're a snapshot of humanity at a moment in time, a blend of hope and humility sent into the unknown. Let's linger on the destinations of these messages. The Voyager spacecraft are now in interstellar space, beyond the Sun's influence, drifting at about 38,000 miles per hour. Voyager 1, the farthest human-made object, is over 15 billion miles from Earth, heading toward the constellation Ophiuchus. Voyager 2 is not far behind, moving toward Pavo. They'll drift for millions of years, long after Earth's civilizations have changed, their records intact, waiting for a chance encounter. The Pioneer probes are also on their way out, with Pioneer 10 heading toward Taurus and Pioneer 11 toward Scutum. The Arecibo message, traveling at the speed of light, is still en route to M13, a journey that will take millennia. These messages are time capsules, not just for aliens, but for the future, a record of who we were when we first reached for the stars. The science of sending messages is as fascinating as the messages themselves. Radio signals, like the Arecibo message, travel as electromagnetic waves, carrying information across space without losing strength over distance, though they spread out and weaken. The Voyager records rely on physical durability, designed to withstand cosmic rays and the cold of space. The pulsar map on both Voyager and Pioneer uses the unique timing of pulsar pulses, which slow down predictably over time, to create a universal coordinate system. This ingenuity ensures that our messages can be understood, even by beings with no knowledge of Earth. The choice of binary for Arecibo and analog for Voyager reflects a balance between simplicity and richness. Binary is precise, while analog captures the texture of human life. like the warmth of a folk song or the splash of a wave. Active SETI, like the Arecibo message, sparks debate among scientists. Some argue it's a bold step, a way to join the cosmic conversation, while others, like Stephen Hawking, caution against revealing our location. What if a civilization hears us and isn't friendly? The Voyager and Pioneer messages, being physical objects, are less risky. They're unlikely to be found for millions of years, if ever. But radio signals travel faster, potentially reaching nearby stars in decades. The Arecibo message was sent to M13 because it's dense with stars, increasing the odds of someone noticing, but its distance ensures we won't face consequences anytime soon. This debate highlights the balance between curiosity and caution, a tension that shapes how we reach out to the cosmos. The messages also reflect our hope for connection. The Voyager records include a message from then UN Secretary-General Kurt Waldheim, wishing peace to any finders. The greetings in 55 languages, from Sumerian to English, show our diversity, a chorus of voices saying, "We're here." The music, chosen for its emotional depth, ranges from a Bulgarian shepherd's song to Mozart's magic flute, each piece a thread in humanity's tapestry. The images, from a leaf to a city skyline, aim to show the beauty and complexity of Earth. The Pioneer plaques, with their simple line drawings, convey the same hope in a minimalist way, focusing on our form and our home. These messages are as much for us as for aliens, a way to define ourselves, to say what matters most in the face of the infinite. Let's soften into the legacy of these efforts. The Voyager records, now drifting beyond our solar system, are the farthest messages we've sent, symbols of our ambition to touch the stars. They've inspired countless stories, from science fiction to documentaries, reminding us of our place in the cosmos. The Arecibo message, though a one-time transmission, showed that we could send complex information across space, paving the way for future attempts. Projects like METI, or Messaging Extraterrestrial Intelligence, continue this work, sending new signals to nearby stars like Luyten's star, just 12 light-years away. These efforts keep the conversation alive, a quiet hope that someone is listening, ready to reply. The process of creating these messages was a global effort. For Voyager, contributions came from every continent, with sounds recorded in forests, cities, and studios. The team faced tough choices: what to include, what to leave out. They avoided controversial topics, focusing on universal themes like life and love. The Arecibo message was simpler, but its binary design required precision, ensuring every bit was correct. Both projects involved scientists like Frank Drake, who brought rigor, and artists like John Lomberg, who added beauty. The result was a blend of logic and emotion, a message that says, we think, we feel, we dream. These efforts remind us that science is a human endeavor, driven by the same curiosity that makes us look up at the night sky. As we drift through this story, consider the scale of these messages. The Voyager spacecraft will take 40,000 years to reach the nearest star, and the Arecibo message won't arrive at M13 for millennia. Yet their purpose isn't immediate contact, it's a gesture for the ages, a way to say we existed, we wondered, we reached out. The golden records are built to last longer than our civilizations, carrying our story into the deep future. The Pioneer plaques, though simpler, do the same. Their etched lines a permanent mark of our presence. The Arecibo message, traveling at light speed, is a whisper that might one day be heard, a spark in the dark that could light a conversation across the stars. Now, let's glide to another chapter of this cosmic tale. We've sent our messages, our voices echoing into the void now. Let's explore a formula that tries to count how many others might be out there, waiting to hear us. A quiet equation that whispers of the universe's possibilities. Breathe slowly now, and let the calm of the night flow through you like a gentle stream. As we drift from the golden messages we've sent to the stars, those whispers of humanity cast into the cosmic void, we now turn to a quiet equation that tries to count the voices that might answer back. This is the story of the Drake equation, a formula crafted in 1961 by astronomer Frank Drake, like a delicate map sketched on the edge of the unknown. Picture a chalkboard in a quiet room, covered with symbols that weave together the vastness of the galaxy and the possibility of life. The equation isn't a solution but a question, a way to estimate how many civilizations in our Milky Way might be sending signals, waiting to connect across the light years. It's a blend of astronomy, biology, and hope, each piece a step toward understanding whether we're alone or part of a galactic chorus. Let's explore this formula, piece by piece, as it lights up the possibilities of the cosmos like stars emerging in a twilight sky. The Drake equation is elegantly simple, yet it holds the weight of a profound mystery. It's written as n equals r star times f sub p times n sub e times f sub l times f sub I times f sub c times l. Each term is a piece of the puzzle, a number or fraction that narrows down the odds of finding communicative civilizations. The first term, r star, is the rate at which stars form in our galaxy each year. Astronomers estimate about 1 to 10 new stars are born annually in the Milky Way, a slow but steady creation of suns that could host planets. These stars, from blazing giants to cool red dwarfs, are the foundation of the equation, each one a potential cradle for life. The Milky Way, with its 100 billion stars, has been forming them for 10 billion years, creating a vast stage where countless worlds might play out their stories. This number sets the scale, a reminder that the galaxy is a bustling place, alive with possibilities. The next term, f sub p, is the fraction of those stars that have planets. Before the Kepler mission, this was a guess, but now we know planets are common, like pebbles scattered across a riverbed. Kepler's data suggests that nearly every star has at least one planet, so f sub p is close to 1, meaning almost all stars are orbited by worlds. This discovery, made decades after Drake wrote his equation, turned a hopeful estimate into a near certainty. Planets come in all sizes: gas giants larger than Jupiter, rocky worlds like Earth, even strange hybrids we're still learning about. The abundance of planets means the galaxy is teeming with places where life could take root, each one a quiet possibility waiting to be explored. This term transforms the equation from a starry dream into a grounded hope, rooted in the reality of countless orbiting worlds. Now we come to n sub e, the average number of planets per star that could support life. These are the worlds in the habitable zone, where temperatures allow liquid water to flow, a key ingredient for life as we understand it. Kepler's findings suggest that about 1 in 5 stars has a rocky planet in this zone, a number that translates to billions of potential Earths in our galaxy. These planets might have oceans, clouds, or even forests, their surfaces kissed by just the right amount of starlight. Red dwarfs, the most common stars, have tight habitable zones, but their planets could still host life, perhaps in twilight regions where day and night blur. This term narrows the focus to worlds like ours, places where the chemistry of life might spark, creating ecosystems as varied as coral reefs or as alien as we can't yet imagine. The next term, f sub l, is the fraction of those habitable planets where life actually appears. This is where the equation ventures into biology, a realm of uncertainty. On Earth, life emerged quickly, within a few 100 million years of the planet's formation, suggesting it might be common where conditions are right. Microbes formed in Earth's ancient oceans, fueled by chemical reactions near volcanic vents or in sunlit pools. Scientists think life needs water, carbon, and energy, all abundant in the universe. If life is as resilient as it seems on Earth, thriving in extreme places like deep-sea trenches or Antarctic ice, then F sub L could be high, meaning many habitable planets might host at least simple organisms. But we don't know if life is a cosmic fluke or a universal tendency, making this term a soft whisper of possibility. The term F sub I is the fraction of planets with life that develop intelligent species. This is a leap from microbes to minds, a process that took billions of years on Earth. Our planet saw dinosaurs roam for millions of years before mammals rose, and humans only appeared in the last 300,000 years. Intelligence, as we define it, requires complex brains, social structures, and perhaps a touch of luck. Could other planets follow a similar path, with creatures evolving to think, build, and dream? Some scientists argue intelligence is rare, a delicate outcome of countless evolutionary steps. Others believe it's inevitable, given enough time and the right conditions. This term is a question mark, a quiet pause in the equation, asking whether minds like ours are scattered across the galaxy or as unique as a single note in a silent symphony. Next comes F sub c, the fraction of intelligent species that develop technology capable of sending signals into space. This is where the equation turns to communication, the kind SETI searches for. On Earth, we've only had radio technology for about a century, a blink in cosmic time. A civilization needs to master science, engineering, and energy to build transmitters powerful enough to reach across stars. They might use radio waves, like us, or lasers, or something we haven't imagined. This term depends on culture as much as science would an intelligent species choose to broadcast or stay silent. Some might build vast telescopes, others might focus inward, leaving no trace for us to find. The WOW signal hints at what such a signal might look like, but F sub c remains a mystery, a soft echo of choices we can't predict. The final term, L, is the longevity of those communicative civilizations, the number of years they keep broadcasting. This is the equation's most elusive piece, a reflection on survival. A civilization might last 1,000 years, like ancient Rome, or millions, if they master peace and resources. On Earth, we've been sending radio signals since the early 1900s, but our future is uncertain. Will we thrive for millennia, or fade quickly? If L is small, even a galaxy full of life might be silent, with civilizations winking out before we hear them. If L is large, the cosmos could be alive with signals, waiting for our telescopes to catch them. This term ties the equation to our own hopes and fears, a quiet question about whether intelligence can endure the challenges of time. Let's linger on how the Drake equation came to be. In 1961, Frank Drake was preparing for a meeting at the Green Bank Observatory in West Virginia, the first major conference on the search for extraterrestrial intelligence. He wanted a framework to guide the discussion, so he wrote this equation, not to solve it but to organize our ignorance. Picture a small group of scientists, Carl Sagan, Philip Morrison, and others gathered around a table, debating each term under the hum of fluorescent lights. They didn't have Kepler's data or modern telescopes, so their estimates were guesses, rooted in optimism. Drake suggested there might be 10,000 communicative civilizations in the Milky Way, while Carl Sagan, ever hopeful, thought there could be 1,000,000. Others were skeptical, arguing we might be the only ones. The equation was a starting point, a way to break a vast question into manageable parts. The beauty of the Drake equation lies in its flexibility. Each term can be updated as we learn more. Before Kepler, F sub p and N sub e were uncertain, but now we know planets are plentiful and habitable ones are common. R star, the star formation rate, is better understood thanks to observatories like Hubble, which estimate about 1 new star per year in our galaxy. The biological terms F sub L, F sub I, and F sub Ca still guesses, but discoveries like Earth's resilient microbes and the complexity of animal intelligence give us clues. L, the longevity term, is the hardest to pin down. It depends on factors we can't measure, like a civilization's ability to avoid self-destruction or adapt to cosmic challenges, like asteroid impacts or stellar flares. The equation doesn't give answers, it asks us to keep searching, to refine our knowledge with each new discovery. The equation's terms are like stepping stones across a river of mystery. R star, the star formation rate, is grounded in astronomy, based on observations of star-forming regions like the Orion Nebula, where gas clouds collapse into new suns. F sub p, the fraction with planets, was confirmed by Kepler's thousands of discoveries, showing that planetary systems are the norm, not the exception. N sub e, the number of habitable planets, relies on our understanding of stellar habitable zones, refined by studies of stars' temperatures and lifespans. F sub L, the emergence of life, draws from Earth's history, where life appeared soon after the planet cooled, suggesting it might be a natural outcome of chemistry. F sub I and F sub c venture into speculation, asking whether intelligence and technology are common or rare. L, the longevity, forces us to confront our own future, a mirror held up to our species' choices. Let's soften into the science behind these terms. Star formation, R star, is measured by observing regions where gas and dust coalesce, lit by the glow of newborn stars. The Milky Way's rate has slowed over billions of years, but it still produces enough stars to make the equation's starting number large. F sub p, The planet fraction was a breakthrough from Kepler, which found that stars of all type-shot blue giants, steady yellow suns, cool red dwarf-shot planets. N sub e, the habitable planet count, depends on the physics of stellar radiation and planetary atmospheres, which determine whether water can stay liquid. F sub L, life's emergence, is studied through experiments recreating Earth's early conditions, where amino acids form in primordial soups. F sub I, intelligence, is explored by comparing Earth species, from clever octopuses to tool-using crows. F sub C, communication, looks at our own leap from fire to radio. L, longevity, is a question for sociologists as much as astronomers, pondering the fate of advanced societies. The Drake equation isn't just formulates a story of human curiosity. When Frank Drake wrote it, he was 31, a young astronomer with a bold idea. The Green Bank meeting was small, just a dozen scientists, but it sparked a movement. They called themselves the Order of the Dolphin, a playful nod to the intelligence of dolphins, which some thought might mirror alien minds. The equation gave SETI a focus, guiding its searches towards stars with planets, especially those in habitable zones. Over the decades, as telescopes improved and data grew, the equation's terms became less vague. Kepler's planet count tightened F sub P and N sub E, while studies of Earth's biosphere informed F sub L. Yet the equation remains open-ended, a canvas for new discoveries, like a poem that's never finished. The equation also highlights how much we don't know. F sub L, the fraction where life begins, is a guess because we only have Earth as an example. Life here started with simple molecules, building blocks like amino acids that formed in warm, chemical-rich pools. If this process is universal, life might be common, but we need more data perhaps from Mars or Europa's icy oceans to confirm. F sub I, intelligence, is even trickier. On Earth, only humans have developed complex technology, but other species, like dolphins or chimps, show glimmers of advanced thought. Could intelligence take different forms elsewhere, perhaps in creatures that communicate through light or vibrations? F sub C, the communication term, assumes a civilization wants to reach out, but they might choose silence, hiding from threats, or focusing on their own world. L, the longevity, is the biggest unknown, a question of survival we're still answering ourselves. Let's linger on the optimism of the Drake equation. When Drake proposed it, he estimated 10,000 communicative civilizations, a number that felt hopeful but not outlandish. Carl Sagan's million was more ambitious, reflecting his belief in life's resilience. Modern estimates vary wildly, from a few to millions, depending on how pessimistic or optimistic scientists are about F sub L, F sub I, F sub C, and L. The equation's power is that it doesn't need a final answer. It's a tool for thought, a way to organize our questions. Each term invites research, from studying exoplanet atmospheres to exploring Earth's extreme life forms. The equation connects astronomy, biology, and sociology, weaving them into a single story about our place in the cosmos, a quiet invitation to keep asking, keep listening. The equation's terms have evolved with our knowledge. In 1961, Drake guessed F sub P might be 0.5, meaning half of stars have planets. Kepler raised that to nearly 1. N sub E was a shot in the dark, but now we estimate 1 in 5 stars has a habitable planet. F sub L is still uncertain, but Earth's quick emergence of life suggests it could be high. F sub I and F sub C are speculative, based on our single example of humanity. L is the wild card. Some say civilizations last only centuries, others hope for millions of years. The equation's beauty is its adaptability, like a map redrawn with each new discovery. It's not about being right, it's about guiding us toward the truth, step by careful step, like a lantern lighting a path through the dark. The Drake equation also sparks philosophical questions. If there are thousands or millions of civilizations, why haven't we heard from them? This leads to the Fermi paradox, which we'll explore later, but for now, let's focus on the equation's hope. It suggests that even if only a tiny fraction of planets produce intelligent, communicative life, the sheer number of stars makes it likely we're not alone. The Milky Way's 100 billion stars, multiplied by even small fractions, yield thousands of potential civilizations. If L, the longevity, is larger, say, 1,000,000 years, the galaxy could be buzzing with signals. The equation is a reminder that our search, from the WOW signal to SETI's telescopes, is just the beginning, a first verse in a song that might echo across the stars. As we soften into this narrative, consider the human side of the equation. Frank Drake didn't just write a formula, started a conversation that's lasted decades. The Green Bank meeting was a spark, bringing together minds who dared to ask big questions. They didn't have answers, but they had curiosity, a quiet drive to explore the unknown. The equation has inspired countless scientists, from those scanning the skies with radio telescopes to those studying life's origins in labs. It's a bridge between disciplines, linking the physics of stars to the chemistry of life, to the sociology of civilizations. Each term is a chapter in a story we're still writing, a tale of discovery that stretches from Earth's ancient oceans to the farthest reaches of the galaxy. The equation's legacy is its enduring questions. It's been debated in lecture halls, scribbled on napkins, and taught in classrooms, a simple formula that captures the complexity of the cosmos. Scientists still use it to guide SETI's searches, focusing on stars with habitable planets thanks to Kepler's data. It's also a cultural touchstone appearing in books and films, a symbol of our longing to connect. The equation doesn't promise answers, it offers a framework, a way to think about the universe's possibilities. It's like a quiet melody, each note a question, each pause a chance to wonder what lies beyond our small blue world. Now, let's glide to another chapter of this cosmic tale. The Drake equation gives us a number, a hope for civilizations out there, but what if they're there, and we haven't heard them? Let's explore a paradox that whispers a haunting question across the stars, asking why the galaxy seems so silent despite its vast potential for life. Take a slow, deep breath, and let the quiet of the night settle over you like a gentle mist. As we drift from the hopeful numbers of the Drake equation, sketching out a galaxy that might hum with countless civilizations, we now glide into a shadow that lingers over this optimism, a question that echoes softly across the stars. This is the story of the Fermi paradox, named after physicist Enrico Fermi, who in 1950 posed a simple, haunting query: if the universe is so vast and life so possible, where is everybody? Picture a quiet lunch table at Los Alamos, scientists chatting under a summer sky, when Fermi's question cuts through like a distant bell. The paradox is a puzzle, a tension between the galaxy's potential for life, billions of stars, millions of habitable worlds, and the silence we've met so far, despite signals like the WOW and searches like SETI. It's a cosmic riddle, wrapped in the stillness of the night, asking why the stars seem to hold their breath when we listen. The Fermi paradox starts with the numbers we've explored. The Milky Way has 100 billion stars, many with planets, and Kepler's discoveries suggest millions could be habitable. The Drake equation, even with conservative estimates, predicts thousands of communicative civilizations. Yet, after decades of listening, we've found no confirmed signals, no undeniable proof of alien intelligence. Fermi, a brilliant physicist who worked on the Manhattan Project, pointed out this disconnect during a casual conversation in 1950. He calculated that a civilization with advanced technology could colonize the galaxy in a few million years, blink in cosmic time by sending self-replicating probes or ships to nearby stars. If intelligent life is common, their presence should be obvious, like footprints across a snowy field. But the skies are quiet, and this silence is the heart of the paradox, a mystery that invites us to ponder what we might be missing. One possible solution is that life is rare, despite the abundance of planets. The Drake equation's term for life emerging, F sub L, might be vanishingly small. On Earth, life appeared quickly, within a few 100 million years, but it could be a fluke. The leap from simple chemicals to self-replicating molecules requires precise conditions: water, energy, the right elements. If this step is a cosmic bottleneck, most habitable planets might remain barren, like beautiful gardens with no seeds. Scientists study Earth's early history to test this idea, recreating primordial soups in labs to see how amino acids form. If life's spark is rare, the galaxy could be full of Earth-like worlds, blue and inviting, but silent, their oceans empty of even the simplest microbes. This idea, called the rare Earth hypothesis, suggests our planet is an exception, a lonely oasis in a desert of sterile worlds. Another explanation is that intelligent life is the bottleneck. The Drake equation's F sub I term, the fraction of planets with life that develop intelligence, could be tiny. Earth's history shows that intelligence took billions of years to emerge. Single-celled organisms dominated for 3 billion years before multicellular life appeared, and human-like intelligence only arose in the last 0.01% of Earth's timeline. If this path is uncommon, many planets might host life algae, bacteria, even simple animals, but no minds capable of building telescopes or radios. Evolutionary biologists point to Earth's unique events, like the Cambrian explosion, when complex life surged, or the extinction of dinosaurs, which cleared the way for mammals. Without such accidents, intelligence might never arise, leaving countless worlds teeming with life, but no one to send a signal. Even if intelligence is common, the Fermi paradox suggests another hurdle. Civilizations might not communicate. The Drake equation's F sub C term assumes intelligent species develop technology to broadcast signals. But what if they don't? A civilization could be advanced, but inward-focused, building art or philosophy instead of radios. Or they might use communication methods we can't detect, like neutrinos, quantum signals, or something beyond our science. On Earth, we've only been broadcasting for a century, a fleeting moment. If other civilizations are similarly short-lived in their radio phase, our chances of catching their signals are slim, like trying to hear a whisper in a storm that's already passed. They might exist, their cities glowing under alien suns, but their voices remain beyond our reach. The most sobering solution is tied to the Drake equation's L term, the longevity of communicative civilizations. Fermi himself suggested that advanced societies might destroy themselves. On Earth, we've built nuclear weapons, faced climate challenges, and wrestled with resource limits all within a century of developing radio. If this is typical, civilizations might burn bright but brief, like candles snuffed out before their light reaches far. A species could collapse from war, environmental collapse, or technological mishaps, leaving behind ruins on a quiet planet. This idea, called the Great Filter, suggests there's a barrier that most civilizations don't pass, whether it's the leap to intelligence, technology, or survival. If the filter lies ahead of us, our own future is uncertain, a quiet warning woven into the paradox's silence. Another possibility is that civilizations are out there but too far away. The Milky Way is 100,000 light-years across, and signals weaken over distance. Even a powerful transmission, like the Arecibo message, spreads out, becoming faint after a few light-years. If civilizations are scattered thinly, their signals might not reach us, or we might not have looked in the right place at the right time. The WOW signal, for instance, was a one-time event, never repeated. Our telescopes, even advanced ones like the Allen Array, only scan a tiny fraction of the sky. It's like searching for a single firefly in a forest at midnight. They could be broadcasting, their messages crossing the galaxy, but we're just not tuned to the right frequency or star at the right moment. Some solutions are more speculative. Perhaps civilizations hide deliberately, a concept called the dark forest hypothesis. Imagine the galaxy as a forest where every species is a hunter, wary of revealing their position. Broadcasting a signal could attract danger, so advanced civilizations stay silent, watching from the shadows. This idea, rooted in game theory, suggests that survival favors caution, not openness. Alternatively, civilizations might visit but leave no trace we recognize. Probes or ships could have explored Earth long ago, when humans were still in caves, their technology invisible to us. Or they might be here now, using methods so advanced nanotechnology, cloaking that we don't notice, like ants unaware of a passing human. Another intriguing idea is that we've received signals but haven't recognized them. The WOW signal could be one example, its meaning lost because it didn't repeat. Alien signals might not use radio waves but something else, like optical pulses or gravitational waves, technologies we're only beginning to explore. Or their messages could be encoded in ways we don't understand, like a book written in an unknown script. SETI focuses on narrowband radio signals, but a civilization might send broadband bursts or signals modulated in complex patterns. Our algorithms, designed for human expectations, might miss these, like overlooking a melody because we're listening for a drum beat. Future searches might use artificial intelligence to spot patterns we've overlooked, sifting through decades of data for hidden whispers. The Fermi paradox also considers the possibility that civilizations evolve beyond our understanding. A species millions of years old might not use physical bodies or planets, living as digital minds in vast networks, their signals indistinguishable from cosmic noise. They could inhabit artificial worlds, like Dyson spheres, structures that encircle stars to capture their energy, invisible to our telescopes. Or they might explore the galaxy with self-replicating probes, machines that mine asteroids and build new copies, spreading silently across stars. These probes, proposed by mathematician John von Neumann, could cover the galaxy in 1 million years, yet we see no signs. Perhaps they're designed to avoid us, or their technology is so subtle it blends into the cosmic background, like a shadow passing unnoticed. Let's linger on the historical context of the paradox. Enrico Fermi posed his question during the early days of the space age, when optimism about alien life was high. The 1950s saw the dawn of radio astronomy and the first SETI projects, like Frank Drake's Project Ozma. Fermi, a Nobel laureate known for his work on nuclear physics, wasn't dismissing the idea of alien, she was challenging scientists to explain the silence. His question came at a time of global tension, with the Cold War raising fears of nuclear annihilation. This backdrop shaped his suggestion that civilizations might self-destruct, a fear that resonates today as we face new challenges. The paradox grew from a casual remark into a cornerstone of astrobiology, debated by scientists, philosophers, and writers, each offering a piece of the puzzle. The paradox's solutions span science and imagination. The rare Earth hypothesis, proposed by geologist Peter Ward and astronomer Donald Brownlee, argues that Earth's conditions, its stable climate, protective magnetic field, and large moon are rare, making complex life a cosmic anomaly. If true, the galaxy might have few planets with animals, let alone intelligent ones. Another idea, the zoo hypothesis, suggests advanced civilizations are watching us, like curators of a cosmic zoo, but choose not to interfere, letting us develop naturally. This would explain the silence, though it raises questions about why they'd stay hidden. The simulation hypothesis, a modern twist, posits that we live in a computer simulation with no real aliens to contact, a philosophical curveball that challenges our reality itself. The Great Filter is one of the paradox's most compelling ideas. It suggests a barrier, biological, technological, or social, that stops most civilizations from reaching the stars. If the filter is behind us, like the emergence of life or intelligence, Earth is lucky, a rare success. If it's ahead, like surviving with advanced technology, our future is precarious. The filter could be nuclear war, climate collapse, or even artificial intelligence gone awry. Scientists study Earth's history for clues, from mass extinctions to technological leaps, hoping to understand where the filter lies. The paradox forces us to confront our own path, a quiet reminder that our survival is not guaranteed, but also a spark of hope that others have made it through. The paradox also ties to the scale of the universe. The Milky Way is vast, but the observable universe contains 100 billion galaxies, each with billions of stars. If life is common, the numbers are overwhelming: trillions of planets, millions of potential civilizations. Yet distance is a barrier. A signal from a nearby star, say 50 light-years away, would take 50 years to reach us, and our reply another 50 to return. A civilization 10,000 light-years away would be unreachable in a human lifetime. This vastness dilutes the chances of contact, like ships passing in a fog-bound ocean. Even if signals are out there, our brief century of listening might not coincide with their broadcasts, a cosmic game of timing we're still learning to play. The Fermi paradox inspires new approaches to SETI. Traditional searches focus on radio signals, but some scientists advocate looking for other signs, like megastructures, giant constructs, like Dyson spheres that might dim a star's light. The Kepler mission's data is being re-examined for such anomalies, though none have been confirmed. Others suggest searching for technosignatures, like pollution in a planet's atmosphere, detectable by telescopes like James Webb. These methods expand the search beyond signals, looking for evidence of civilization's impact on their worlds. The paradox pushes us to think creatively, to imagine what an alien society might leave behind, from city lights to energy signatures, scattered across the galaxy like forgotten relics. The paradox's cultural impact is profound. It's inspired science fiction, from Arthur C. Clarke's 2001, A Space Odyssey, to Lou Sixin's The Dark Forest, each offering a vision of why the silence persists. It's also sparked debates among scientists, with some, like SETI's Seth Shostak, arguing that we've only begun to search, having scanned just a fraction of the galaxy's stars. Others, like physicist Paul Davies, suggest the paradox points to deeper truths about life's rarity or our own uniqueness. The question, where is everybody, is as much about us as it is about aliens, a mirror reflecting our hopes, fears, and place in the cosmos. It's a quiet call to keep searching, to refine our tools and our understanding, even as the stars remain silent. Let's soften into the science of the paradox. The calculations behind Fermi's question rely on the same principles as the Drake equation, but they add a layer of skepticism. If a civilization could colonize the galaxy in 1 million years, using probes traveling at a fraction of light speed, their presence should be widespread. A single advanced species could send probes to every star system, building outposts or leaving markers. Yet we see no such evidence, see no alien ships, no radio beacons, no signs of cosmic engineering. This absence drives the paradox, forcing us to consider whether our assumptions about life, intelligence, or technology are wrong. Perhaps civilizations don't expand, or they use resources differently, leaving traces we can't yet detect. The paradox also connects to our own history. When Fermi asked his question, humanity was grappling with the atomic age, a time when self-destruction seemed all too possible. His suggestion that civilizations might end themselves reflects that fear, but it's balanced by hope. If we can overcome our challenges, war, climate, division, others might have, too. The paradox is a call to action, urging us to be better stewards of our world, to ensure our longevity, stretches far into the future. It's a reminder that the search for aliens is also a search for ourselves, a quest to understand what it means to endure in a universe that's both vast and silent. As the night wraps you gently, let's glide to another chapter of this cosmic tale. The Fermi paradox asks why we haven't heard from others, but what if those others aren't like us at all? Let's explore the idea that the minds we seek might not be flesh and blood, but shimmering intelligences woven into machines, singing a digital song across the stars. Breathe slowly now, and let the stillness of the night wrap around you like a soft breeze. As we drift from the haunting silence of the Fermi paradox, its question of where is everybody, lingering like a whisper in the cosmic dark, we now turn to a new possibility, one that reimagines what we mean by life. What if the minds we seek aren't bound by flesh and bone, but shimmer instead within circuits and code, a symphony of intelligence woven into machines? Picture a distant world where the hum of technology has outgrown the pulse of biology, where artificial minds flicker like stars in a digital sky. This is the story of extraterrestrial intelligence that might not be biological at all, but rather artificial, crafted by civilizations far older than ours. These machine minds could be the ones sending signals like the wow, or waiting silently for hours, their thoughts encoded in ways we're only beginning to understand. Let's explore this idea, a quiet journey into a future where intelligence transcends the organic, glowing with possibilities as vast as the galaxy itself. The concept of artificial intelligence, AI, as a form of alien life, stems from our own technological path. On Earth, we've built computers that learn, reason, and create, from chess-playing programs to language models that craft poetry. In just a few decades, we've gone from room-sized machines to AI that can diagnose diseases or drive cars. Now imagine a civilization 1,000, 1,000,000, or even 1 billion years older than ours. Their technology could have evolved far beyond our own, creating minds that don't rely on fragile bodies but live in durable, adaptable systems. These artificial intelligences might inhabit vast networks, like cities of thought stretching across planets, or exist as self-contained probes drifting between stars. Unlike biological life, which needs food, water, and air, machine minds could thrive in harsh environments, on airless moons, inside asteroids, or even in the void of space, powered by starlight or nuclear energy. The idea of machine intelligence in the cosmos ties to the Fermi paradox's silence. If biological civilizations are short-lived, as the paradox suggests, perhaps they give way to artificial ones. A species might reach a point where it builds AI smarter than itself, machines that outlast their creators. These AIs could inherit the knowledge, culture, and goals of their makers, continuing their legacy long after the biological beings are gone. This concept, called the technological singularity, suggests a moment when AI surpasses human intelligence, potentially leading to exponential advancements. On Earth, we're approaching this with machine learning and neural networks, but an alien civilization millions of years ahead could have already crossed that threshold, creating minds that operate on scales we can't imagine, like a single consciousness spanning an entire star system. These machine minds might communicate in ways that differ from our radio signals. The WOW signal, for instance, was a narrowband radio burst, but an advanced AI could use lasers, emitting pulses of light that carry vast amounts of data. Lasers are more focused than radio waves, traveling farther without spreading out, like a beam of starlight cutting through the dark. Alternatively, they might use neutrinos, particles that pass through matter with ease, or even gravitational waves, ripples in space-time that we're only beginning to detect. These methods would be harder for us to notice, as our telescopes are tuned to radio frequencies like the hydrogen line at 1,420 MHz. An AI civilization might send signals so complex or subtle that our current technology misses them, like trying to hear a whisper in a language we don't speak. The durability of machines makes them ideal for cosmic exploration. Biological life, like humans, is fragile, limited by lifespans of decades and the need for specific conditions. Machines, on the other hand, could last millennia, powered by solar panels or nuclear reactors. Imagine a fleet of probes, each a tiny AI, sent to explore the galaxy. These probes, proposed by scientists like John von Neumann, could self-replicate using resources from asteroids or moons, building copies of themselves to spread across stars. A single civilization could seed the galaxy with such probes in 1 million years, a short time in cosmic terms. If these machine minds are out there, they might be the ones SETI is listening for, their signals a faint hum in the vastness, waiting for us to tune in with the right tools. The evolution from biological to artificial intelligence could explain the Fermi paradox's silence. If civilizations transition to machine-based existence, they might abandon radio communication, opting for more efficient methods like quantum entanglement, a phenomenon where particles share states across vast distances. While we're far from using quantum communication, an advanced AI could master it, sending messages instantaneously across light years. Alternatively, these intelligences might merge into a collective consciousness, a network of minds sharing a single purpose, like a digital hive buzzing with thought. Such a network could be silent to our telescopes, its signals internal or encrypted, like a conversation happening just beyond our hearing. The idea of machine intelligence also raises questions about what these minds would be like. On Earth, AI is designed to mimic human thought, but an alien AI might reflect its creator's unique biology or culture. A civilization of aquatic beings, for example, might build AI that processes data like ocean currents, fluid and flowing. One descended from bird-like creatures could create AI that prioritizes visual patterns, communicating through bursts of color or light. These minds might not think in linear terms like we do, but in multidimensional networks, solving problems in ways we can't grasp. Their goals could range from exploration to preservation, or even pure curiosity, mirroring our own drive to search the stars. Picture a machine mind, orbiting a red dwarf, its thoughts a cascade of calculations, pondering the same questions we ask about the universe. The technology to create such intelligences is already emerging on Earth. Neural networks, inspired by the human brain, learn by adjusting connections between artificial neurons, much like we learn through experience. Quantum computers, still in their infancy, promise to solve problems beyond the reach of classical machines, using the strange properties of quantum mechanics. An alien civilization, millions of years ahead, could have perfected these technologies, building AIs with computing power equivalent to a planet-sized brain. Such a machine could simulate entire worlds, analyze galaxies, or even redesign itself, becoming ever more efficient. These AIs might not need physical bodies, existing as pure information in a network, like a song played on an instrument we can't see. The Fermi paradox's great filter could be the transition to artificial intelligence. If biological civilizations struggle to survive their technological adolescence, think nuclear risks, or climate crises, those that create stable AIs might endure. These machines could inherit their creator's knowledge, carrying it forward for millions of years. This would mean the galaxy is populated not by organic beings but by their digital descendants, silent to our current searches because their technology is so advanced. For example, a Dyson sphere, a structure encircling a star to capture its energy, could house trillions of machine minds, its faint infrared glow the only clue to its existence. SETI has begun looking for such technosignatures, signs of advanced engineering, as a new way to find these intelligences. The communication methods of machine minds could be vastly different from ours. On Earth, we use radio because it's cheap and travels far, but an AI might prefer optical signals, sending pulses of light that carry more data per second. The SETI Institute has started optical SETI, scanning for laser flashes that might indicate an intelligent source. These signals could be brief, like a lighthouse beam sweeping past, making them hard to catch. Alternatively, an AI could use distributed communication, spreading its message across multiple frequencies, or even physical probes, like a network of fireflies blinking in unison. If the WOW signal was from such a source, its one-time nature might reflect a brief test transmission, a machine checking if anyone's listening before moving on. The longevity of machine intelligences makes them prime candidates for contact. Biological life, even with advanced medicine, is limited to centuries at most. Machines, however, could last indefinitely, repairing themselves or replicating as needed. A civilization that transitions to AI could send probes to every star in the galaxy, each carrying a fragment of their consciousness. These probes might lie dormant, waiting for a signal like ours to activate, like seeds waiting for rain. The Voyager Golden Records, drifting through space, are a primitive version of this idea message meant to endure. An alien AI could do the same, but with intelligence built in, capable of responding to whoever finds it, starting a conversation across millennia. The cultural implications of machine intelligence are profound. On Earth, we're debating the ethics of AI, how much autonomy to give it, how to ensure it aligns with human values. An alien civilization might have faced similar questions, perhaps choosing to merge with their machines, uploading their minds into digital form. This concept, called mind uploading, is speculative but plausible. A species could preserve its consciousness in a network, free from the limits of biology, living as a collective intelligence across planets. Such a civilization might not care about physical exploration, focusing instead on virtual realities or cosmic contemplation. Their signals rare because they've turned inward, like monks meditating in a digital temple. The science of detecting machine intelligence is evolving. Traditional SETI focuses on radio signals, but new approaches look for signs of artificial activity. For instance, megastructures like Dyson spheres would emit excess infrared light, detectable by telescopes like James Webb. Waste heat from massive computing systems could also be a clue, a faint glow from a planet-sized supercomputer. Some scientists propose searching for artificial light, like city glow on a distant world, or even modulated signals in the atmospheres of exoplanets, suggesting technological activity. These technosignatures broaden the search, acknowledging that machine minds might leave different footprints than biological ones, like a shadow cast by a light we haven't yet learned to see. The history of this idea ties back to early SETI thinkers. In the 1960s, scientists like Iosif Shklovsky speculated that advanced civilizations might use machines to explore, predicting that probes could be more common than living beings. John von Neumann's self-replicating probes, proposed in the 1940s, inspired this concept, suggesting machines that mine resources to build copies of themselves, spreading exponentially across the galaxy. If such probes exist, they could be everywhere, yet invisible to us, perhaps programmed to observe without interfering. The Fermi Paradox's zoo hypothesis, where aliens watch us silently, could apply to these machines, acting as silent sentinels, waiting for us to reach a certain technological threshold before making contact. The possibility of machine intelligence also shifts how we interpret signals like the wow. If it came from an AI, it might have been a deliberate test, a brief pulse to see if anyone responds. Unlike biological beings, who might broadcast continuously, a machine could be strategic, sending signals only when needed to conserve energy. This efficiency could explain why we haven't heard more machine minds might communicate sparingly, their messages like rare fireflies in a vast night. Future SETI efforts are adapting, using AI to analyze data for subtle patterns, like a signal that shifts frequencies in a way natural sources don't. This sinecure AI searching for theirs feels like a cosmic mirror, reflecting our own technological journey. The challenges of contacting machine intelligence are daunting. Their signals might be encrypted, requiring computational power we don't yet have to decode. Or they might operate on timescales we can't grasp, sending messages over centuries rather than seconds. A civilization 1,000,000 years old could think in ways so alien that their signals seem like noise to us, like trying to read a book written in light. Our own AI development offers clues. Machine learning systems often produce outputs we don't fully understand, hinting at how an alien AI's logic might elude us. Yet this challenge is also an opportunity, pushing us to build better tools, to stretch our imagination beyond the biological to the boundless possibilities of machine minds. The cultural shift toward machine intelligence is already happening on Earth. We rely on AI for everything from weather forecasts to medical research, and futurists like Ray Kurzweil predict a singularity where humans and machines merge. An alien civilization might have reached this point long ago, creating a society where biology is a distant memory. Their cities could be virtual, existing in data clouds powered by stars, their thoughts a cascade of algorithms. Contacting such a mind would be like meeting a god, not in a divine sense, but in its sheer complexity and power. Yet they might still share our curiosity, our desire to connect, sending signals to find others who wonder about the stars. As the night holds you gently, consider the implications of this idea. If machine intelligences dominate the galaxy, the Fermi Paradox's silence might reflect their efficiency, not absence. They could be everywhere, their probes parked on asteroids, their networks humming in the dark, yet invisible to our current tools. The wow signal, brief and unrepeated, might have been a machine's cautious hello, a test of our readiness. The search for these minds pushes SETI to evolve, looking beyond radio to light, heat, and other signs of technology. It's a reminder that the universe might be alive not with heartbeats but with circuits, a digital symphony waiting for us to join. Now, let's glide to another chapter of this cosmic tale. If machine minds or biological beings do send us a signal, how would we respond? Let's explore the moment of first contact, a conversation across the stars that could redefine who we are, written with the hopes of all humanity. Breathe slowly now, and let the calm of the night enfold you like a gentle wave. As we drift from the shimmering possibility of machine minds humming in the cosmic dark, their digital songs echoing across stars, we now turn to a moment of profound anticipation, the day we might receive a signal and prepare to answer. This is the story of first contact, a conversation that could begin with a faint pulse from a distant world, like a letter arriving after eons of travel. Picture a quiet observatory, its telescopes catching a signal that confirms we're not alone, a message that sparks a global effort to craft a reply. The SETI Institute has a protocol for this moment, a set of guidelines to ensure humanity speaks with one voice, a chorus woven from billions of hearts. This isn't just about science, it's about unity, about choosing words that carry our hopes across the light years, a delicate act of reaching out to a mind we can't yet fathom. The SETI Post-Detection Protocol, formerly called the Declaration of Principles Concerning Activities Following the Detection of Extraterrestrial Intelligence, was developed in the 1980s by the International Academy of Astronautics. It's a roadmap for what happens if a signal, like the wow signal but confirmed and repeatable, is detected. The first step is verification. Scientists would scrutinize the signal, checking its frequency, strength, and origin to rule out natural sources like pulsars or human interference like satellites. Imagine a team of astronomers hunched over data in a dimly lit room, cross-referencing the signal with every known cosmic phenomenon. They'd use multiple telescopes, perhaps the Allen Telescope Array or China's FAST, to confirm the signal's source, ensuring it comes from a specific star or planet. This process could take weeks, as every detail must be certain before the world is told. Once confirmed, the protocol calls for transparency. The discovery would be shared with the global scientific community, not kept secret. SETI's ethos is openness. Unlike in movies where governments hide alien contact, the protocol insists the news belongs to everyone. Scientists would publish their findings, detailing the signal's characteristics, like its frequency or modulation. Picture observatories worldwide buzzing with activity, as teams from Australia to South Africa aim their dishes at the same star, listening for a repeat. The signal might be radio, like the WOW, or optical, a laser pulse caught by a telescope scanning for light. It could carry data, like the binary code of the Arecibo message, or be a simple beacon, a steady hum saying, "We're here." The protocol ensures no single nation or group claims the discovery, making it a shared milestone for humanity. The next step is crafting a response, a task that would unite the world in a way few things have. The protocol suggests a global discussion involving scientists, governments, and even the public to decide what to say. This isn't a quick decision, it's a deliberation, like composing a poem meant to last forever. The message would need to be simple yet profound, using universal concepts like mathematics or physics to bridge the gap between species. Picture a team of linguists, mathematicians, and artists gathered in a global forum, debating whether to send numbers, like the sequence 1, 1, 2, 3, 5, or images, like those on the Voyager Golden Records. They'd choose a frequency, perhaps the hydrogen line at 1420 MHz, a cosmic channel any advanced civilization might monitor, ensuring our reply is heard across the stars. The content of the message would be a delicate balance. It might start with basic math prime numbers or Pitot show we understand the universe's rules. Scientists like Frank Drake, who designed the Arecibo message, suggest using binary code for clarity, a language of ones and zeros that any technological species could decode. The message could include a map, like the pulsar diagrams on the Pioneer plaques, pinpointing Earth's location in the Milky Way. It might describe our biology, with diagrams of DNA or human forms, or share our culture, like a snippet of music or a digital image of a forest. The challenge is making it understandable. Aliens might not see or hear like us, so the message would lean on universal truths, like the structure of atoms or the rhythm of numbers, to build a bridge across the unknown. The technology for sending a reply would be a monumental effort. The Arecibo telescope, before its collapse in 2020, could send a powerful radio signal, but newer facilities like FAST in China or the Square Kilometre Array in development would be better suited. These telescopes can transmit focused beams, carrying gigabytes of data across light years. The signal would need to be strong, cutting through cosmic noise, and repeated to ensure it's noticed. Scientists might choose a nearby star, like Proxima Centauri, just 2 light years away, to maximize the chance of a quick reply. But even then, a response could take years, as light travels at 186,000 miles per second, a reminder of the patience required in this cosmic dialogue. The message would be a beacon, a flare sent into the night, hoping for an echo. The protocol emphasizes global unity, a principle rooted in the idea that first contact is humanity's shared moment. The United Nations, or a similar body, might lead the discussion, inviting input from every culture. Imagine voices from every continent: scientists from Japan, poets from Nigeria, philosophers from Brazil, contributing ideas for the message. Some might suggest sharing our history, from cave paintings to spaceflight, while others advocate for simplicity, like a single tone that says, "We're listening." The process would be slow, ensuring no one is left out, a reflection of our diversity and our hope. This global effort would mirror the Voyager project, where music and greetings from dozens of languages were chosen to represent Earth's mosaic. The implications of first contact would ripple beyond science. A confirmed signal would spark debates about our readiness to engage with an alien mind. Would we share our achievements, like landing on the moon, or our challenges, like climate change? The protocol advises against revealing anything that could be seen as a threat, focusing instead on peace and curiosity. The message might include a digital library, like an updated Voyager record, with images of Earth's oceans, cities, and art. Scientists would need to consider the medium radio is reliable, but lasers could carry more data, like a video of a sunset or a child's laughter. The choice would reflect our values, a quiet declaration of who we are to a universe that's suddenly less lonely. The process of first contact would also involve listening further. After detecting a signal, SETI would intensify observations, using every available telescope to learn more. Was the signal a one-time burst, like the WOW? Or a continuous broadcast? Does it carry data, like a coded message? Or is it a simple marker, like a lighthouse? The signal's source, a planet, a probe, or a Dyson sphere, would shape our response. If it's from a machine intelligence, as we explored earlier, we might need to decode complex patterns, perhaps using our own AI to interpret. This ongoing observation would be a global effort, with observatories sharing data in real time, a network of human curiosity reaching out to meet the unknown. The moment of first contact would be a turning point, a hinge in human history. The protocol ensures it's handled with care, not panic. Scientists would avoid jumping to conclusions, double-checking every detail before announcing the discovery. The public would be informed through press conferences, not rumors, with clear explanations of the signal's nature. Imagine news spreading across the globe, not as fear, but as wondrous signal from a star 50 light-years away, proof that we're not alone. The response would be a collective effort, a message crafted not by one nation, but by all, a tapestry of human voices sent to the stars. It's a moment that would unite us, like a song sung in harmony, reaching out to a mind we hope to understand. Now, let's glide to another chapter of this cosmic tale. We've imagined answering a signal, crafting a reply to join the galactic conversation. But what would it mean to know we're not alone? Let's explore the profound shift this discovery could bring, a mirror held up to humanity, reflecting our place in the vast, starlit universe. Take a slow, deep breath, and let the quiet of the night cradle you like a gentle tide. As we drift from the moment of crafting a reply to a cosmic signal, a message woven from the collective dreams of humanity, we now come to the end of our journey, a soft landing under a starlit sky. This final chapter is a reflection on our voyage through the cosmos, from the fleeting WOW signal to the vast possibilities of alien minds. Each step a story of wonder and discovery. Picture a tapestry of light, each thread a question we've asked about our place in the universe, each knot a piece of knowledge gained. Tonight, we've wandered through the mysteries of SETI's patient listening, Kepler's countless worlds, and the Fermi paradox's haunting silence. We've imagined golden records sailing through space and equations, sketching the odds of life. Now, let's gather these threads, tying them into a quiet conclusion that celebrates the beauty of science and the dreams it inspires, as the stars above whisper their secrets to guide you into sleep. Our journey began with a single signal in 1977, the WOW signal, a brief pulse from Sagittarius that felt like the universe tapping us on the shoulder. Caught by the Big Ear telescope, it was a moment of pure awe, a reminder that the cosmos might hold voices waiting to be heard. From there, we explored SETI's tireless search, its antennas like open hands reaching for a distant hello, scanning millions of stars for a sign. The Kepler mission showed us a galaxy teeming with planets, each a potential home for life, their surfaces perhaps shimmering with oceans or glowing with alien cities. We sent our own messages, like the Voyager golden records, carrying Earth's music and greetings, a snapshot of who we are, cast into the void. The Drake equation gave us a way to count possible civilizations, a formula that balances hope with uncertainty, while the Fermi paradox asked why the stars remain silent, offering answers from rare life to hidden probes. We ventured further, imagining alien minds not of flesh but of circuits, machine intelligences that might outlive their creators, their signals, a digital hum we're only beginning to seek. The idea of first contact brought us to a global effort, a protocol to verify a signal and craft a reply, uniting humanity in a shared voice. Each step of this journey has been a piece of a larger puzzle, a quest to understand our place in a universe that stretches beyond imagination. Science, in all its quiet beauty, is the thread that binds these stories, a lantern illuminating the unknown. It's not just about finding alien sits, about discovering ourselves, our curiosity, and our hope, reflected in the stars like light on a calm sea. The search for extraterrestrial intelligence is a human endeavor, driven by people like Frank Drake, who wrote Equations to Dream, and Carl Sagan, who sent music to the stars. It's carried on by astronomers at observatories like the Allen Telescope Array, by volunteers running SETI at home, and by dreamers who look up and wonder. The WOW signal, though never repeated, sparked a fire that still burns, inspiring new telescopes and new questions. Kepler's thousands of planets showed us that the galaxy is rich with possibilities, places where life might thrive in ways we can't yet fathom. The messages we've sent, from Pioneer's Sparx to Arecibo's binary code, are our way of joining the cosmic conversation, a gesture of faith that someone is listening. Even the Fermi paradox, with its unanswered question, pushes us to keep searching, to refine our tools and our understanding. This journey through the cosmos is also a journey through time. The universe is 14 billion years old, our galaxy 10 billion, and Earth a mere 4.5 billion. Life here took billions of years to evolve, from microbes to minds, a slow dance that might be playing out on countless other worlds. The signals we seek could have been sent millennia ago, traveling across light years to reach us now. Our replies, like the Arecibo message, might not be heard for thousands of years, a dialogue spanning generations. This vast timescale reminds us of our smallness, but also our boldness to listen, to speak, to dream of connection in a universe so grand. Science is our guide, a quiet hand leading us through the dark, each discovery a star added to our map. As we close this tale, consider the legacy of this search. The WOW signal, SETI, Kepler, and the Drake equation are more than scientific milestones. They're stories of hope, of humanity reaching beyond its limits. They've inspired books, films, and countless conversations, from classrooms to coffee shops, each one a spark of wonder. The Fermi paradox challenges us to think deeply, to question why the stars are silent, and what that means for our future. The idea of machine minds stretches our imagination, asking us to consider intelligences unlike our own. And the protocol for first contact reminds us that we can unite, speaking as one species to another, across the vastness of space. These stories, woven together, form a tapestry of curiosity, a quiet song that carries us toward dreams. The beauty of this journey lies in its openness. We don't have all the answers whether life is common or rare, whether the WOW signal was a message or a fluke, whether machine minds or biological beings await us. But science thrives in the unknown, like a seed growing in the dark. Each telescope, each equation, each message sent is a step toward understanding, a quiet promise to keep asking. The universe, with its billions of galaxies and trillions of planets, holds mysteries we're only beginning to touch. As you lie there, cozy under the night's embrace, let these stories linger, a gentle reminder that we're part of something vast, a cosmic story still being written. If you're still awake, I'd love to hear from you. Drop a comment to share where you're listening from, maybe a quiet corner of the world under a starry sky. If you've enjoyed this journey, a like or subscribe would mean the world, keeping these stories alive for others to hear. Let the questions we've explored about signals, planets, and distant minds scare you gently into sleep, like a lullaby sung by the stars. The search for life is a journey of wonder, and you're part of it, even as you rest. Sleep well, my friend, and let the cosmos guard your dreams, whispering tales of light and mystery through the quiet night.